Welcome to saitechinfo, dear UPSC, TNPSC, NEET and JEE aspirants and school and college students.
Hi students, in this session I'll be explaining about the resolving power of an optical device, optical instrument like telescope, microscopes, etc. The resolving power means, now let me imagine a telescope where I have the resolution of I'm watching a planet, and you suppose if these two either planet or stars, they are overlapping each other, then I can say it is not at all resolved. Are you able to follow? You can look at the first picture. So this is not resolved, means it is almost mixing together, because by distant vision it is almost a double star. It looks like a double star. Okay, right. Now when it is when I am able to resolve it further, I am able to identify two stars. That is partly resolved. That is the second image. When you look at the third image, you are able to distinctly see two stars, okay, or two heavenly objects very clearly. So this is called a fully resolved image. Do you understand? So this resolving power is equal to 0.61 lambda f divided by A. Now this for example, that is, you can multiply by 2 on the numerator as well as the denominator. Therefore R is equal to, we can say RO is equal to, or approximately equal to 1.22 lambda f divided by, instead of A, 2A, right? Okay. Then, and this as I already mentioned, when that is, it can be interpreted as A also instead of 2A. So it is a 0.66 lambda f divided by A. So the resolving power in this case is, that is 1 divided by the lambda into D. That is equal to 2 into mu sine P whole divided by 1.22 lambda. Now look at this mu sine B, that is the numerical aperture, that is called numerical aperture. So the resolving power is equal to 2 into mu sine beta whole divided by 1.22 lambda, where mu represents the refractive index. Beta is called the half angle of the cone of light. That is called half angle of cone of light, and that is from one of the objects. When you look at this picture, you can find this here. This is beta and this is whole theta, and this is the half angle of the conical objective here. Okay, so I am viewing the object like this, and this is the image plane. This is the image plane, and beta is nothing but half of theta, that is half angle. Therefore wavelength is that is an important factor here that decides the resolving power. And the refractive index of the medium is also very significant, that is given by mu. Then half angle, that is half angle of cone of light. It's called half angle of cone of light, and that is given as what? Beta. So the resolving power is the reciprocal of d theta, that is the change in angle. For instance, the smallest angular separation between the two distinct objects, that is S1 and S2. We have seen two distinct objects. In poor resolution, it is overlapping. In a better resolution, you can find the smallest distance between these two. So that is the smallest angular separation. Okay, right. And D is, for instance, let me have a simple diagram. S1 is one of the source and S2 is another one. So we have got these two objects. So when we view like this, there is a small, infinitesimally small angle between these two, and that is called the d theta. And d is the diameter of the objective lens. Okay, so and that d divided by 1.22 lambda is called the resolving power. Okay, so this is one of the important questions frequently asked in any test or examination based on wave or ray optics. Then I would like to add some more thing here. You should know something about optical activity. Optical activity means, for instance, normal light will be vibrating, that is perpendicular to the direction of propagation of light, and that is why we say it is a transverse wave. Light wave is a transverse wave. For example, the light goes like this. Okay, now it will be vibrating like this perpendicularly, and in this angle, in this angle, in this angle. So all perpendicular to the progress of the light. Are you able to follow? And now let me have a circular plane perpendicular to the propagation of light. So that is indicated here. So they are vibrating in all direction. For example, assuming that this is moving towards the y-axis, means along x-axis and z-axis they will be vibrating. Now when it is passed through, such a normal light is passed through a prism called Nicol prism, what happens here? They get separated, and they are called plane polarized light. For example, you have got this vertical vibration, horizontal vibration. When it is passed through the Nicol prism, what happens? It gets separated. So vertical vibration will be moving here, and horizontal vibration will be moving here. Okay, so it means that is they are plane wise polarized, and that is why they are called plane polarized light. When such plane polarized light is passed through, for example, any sugar solution or any optically active compound solution, then they get rotated. They are rotated either towards right or left. If the plane polarized light is rotated towards right, then it's called dextro-rotatory. When it is rotated towards left, it's called levo-rotatory. Are you able to understand this? Right. Now, look at this. Here, the intensity of the light, I, is proportional to cos squared theta. Then you can introduce the constant here, proportionality constant, I naught. So, I is equal to I naught into cos squared theta. This I naught is nothing but the intensity of the polarized light after passing through the polarizer. Are you able to follow? Right. And assuming that when theta is equal to 0, then cos 0 is equal to 1, cos squared theta is equal to 1. Therefore, I is equal to here I naught into 1, that is I is equal to I naught. It means that is when there is no difference between the intensity of the incident light and the polarized light. But when theta is equal to 90, that is when polarized light is perpendicular, then absolutely there is no intensity. I becomes a 0 because cos 90 becomes a 0. Are you able to follow? And that is why in polarized lights and polarized camera or polarized Polaroid that is a lenses, you can totally cut one plane polarized light totally. For example, assuming that this is the Nicol prism, the polarizer, and you have got the plane polarized light like this. If it goes like this, it allows. But when the plane polarized light is in this way, it blocks totally. It is at normal, is it not? So when they are normal, that is 90 degree, it totally blocks the horizontal vibrations. Are you able to follow? So this is the concept here behind the polarizer and analyzer and the polarimetry. Then you know very well about this important thing, that is IB here plus R. is equal to pi by 2. So this pi by 2, from this pi by 2 is nothing but 90, is it not? So pi by 2 is 90 degree. IB plus R is equal to here 90. Therefore, R is equal to 90, that is pi by 2 minus IB. Right? According to Snell's law, refractive index is a constant. It is the ratio between sine of angle of incidence and the sine of angle of refraction. Now, what is the IB? You have got that is the incidence here, incident angle. So, sine of IB divided by sine of R is equal to mu. And instead of R, you can introduce pi by 2 minus IB. And sine 90 minus IB is equal to cos B, is it not? So you can introduce cos IB. So sine IB divided by cos IB is equal to tan IB. So mu is equal to tan IB, and this is called that is Brewster's law. Okay, so these are all very important. So we have discussed in today's session the two important aspects. One is the resolving power of an optical instrument, either a telescope or a microscope. Secondly, we have discussed about polarimetry, that is what is optical activity and what is Brewster's law. Okay, so thank you very much for watching this video.
யாம் பெற்ற இன்பம் பெருக இவ்வையகம் என்பதற்கேற்ப please subscribe if you like our educational contents and share with your family and friends. Thank you for spending your valuable time.